Okay, recording. So if you're wondering where you get the supplemental information, everyone's courses should have received an announcement from Jennifer Stebick about preparations for the midterm exam during recitation, the majority of you. So I will point out, there's some new procedures here because they are in recitation. I encourage you to do the Respondus test browser quiz before going into recitation. Just because it worked last year doesn't mean it's going to work now, so just test it before you get into recitation, because we only have a 5-minute buffer. The exams are 50 minutes, but recitation's 55 minutes. So if you can't get it figured out in 5 minutes, then you're in trouble. So do test with that Respondus test browser quiz in each of your courses. So where you get the supplemental information is in Jennifer's lovely announcement that talks about the procedures here. And so here you see right here, supplemental information is right there for in tips for success. So you will see exactly everything that you will receive at the exam. You might have noticed that some of the practice midterms, it may seem like, oh, not enough information is given, maybe like a constant or something. It most likely is on this supplemental information. So I encourage you, when you're doing the practice exams, to have this supplemental information right in front of you so you know exactly where your eyes need to look to find the zeroth order kinetic integrated rate law, first order, second order, etc. All right, because 50 minutes isn't a lot of time. Let's save as much time if you know where everything is on our supplemental information. See, that's where it is. Okay, he's not looking. So that's where it is. All right, so let me go back to my thing. All right, so I have, everyone hopefully has that document, and then people on Zoom, 117 of you, please right now change your 2-line in your chat box to everyone. And actually, this is the second time someone told me to slay this week, and I responded in the chat box, but I only responded to myself, so I said me. I'm ready to slay. All right. So direct all chat questions to everyone, but make sure the Zoom people, everyone, how many people are in this room? Probably like 250 at least. Everyone can see what you write, so don't write anything inappropriate. And then finally, I already started recording. I will be posting this video on YouTube tonight, so if you have to leave early or if you have a friend who can't make it, that YouTube link is right here at the top of this same packet. I made it super easy to find everything, so that's where the recording will go and anyone can access it. I'm currently in a YouTube subscriber battle with my brother-in-law, so if you could subscribe to my channel, that would be great, so I can beat him. Okay, I don't monetize or anything. I think that's not ethical, but that'd be cool if you could subscribe to me. Okay, so, but shh, don't tell him. All right, so let's get started. What chapter do we want to start on? What topic? Okay, they're just taking selfies. Thought that was a hand. Anything? Yeah. Vapor pressure. Okay, yeah, let's talk about vapor pressure. So let's skip down to question 8. All right. So all these concepts are interrelated. So, most of us came from Chemistry 1210, where we, in chapter 4, we looked at aqueous solutions, we looked at net ionic equations, all that jazz. Those are basically the basics of solution chemistry. But now in this chapter, chapter 13, we are looking at the nitty-gritty details of solution chemistry. What are the different properties and how do the properties of water change when we start adding stuff to water? So let's just think about this conceptually. Most of you have taken Chem 1210 exams before. Is it all math questions? Our exams? Nah. It's like equal concepts and math. So think about what you do best at. I don't know, so think about that. But in the end, concepts are just as important as the math. But the beauty and why I love chemistry is that the concepts always match the math. And I love when those two things intermingle. So let's think about the details that happen when we dissolve something in water. So let's say as the moles or concentration of a non-volatile solute. So an example of a non-volatile solute would be like salt, sugar. All right, so we're making like salt water solution, sugar water solution. A volatile solute would be like water and ethanol, where both of them exert a vapor pressure. All right, so we have a salt water solution. The components are salt and water. What changes as we increase the concentration of salt, as we make the water more salty? How does the mole fraction of water change as we increase the concentration of salt? Mole fraction of water changes how? It goes down. So if you're confused about that, let's back it up a little bit. If I have a pure sample of water, pure water, what is the mole fraction of water? If you have pure water, the only thing is water, it's 1. Yeah, mole fraction of a pure water sample is 1, because the equation for mole fraction is for water would be moles of water in your sample over total moles of substance. So if you just have water, it's the same number divided by one another. So it's 1. But once we start adding salt, we're adding moles of something else. So how does mole fraction change? Once it's not a pure sample of water, it's going to decrease. Yes, it's going to decrease. And so what we see from Raoult's law, the vapor pressure above a water sample is equal to the mole fraction of your water times the pressure of pure water, the vapor pressure of pure water. All right. So if we think about it, like let's say you have a pure water sample, I'm making up a number. Let's say pure water has a vapor pressure of 100 torr. If the water sample is pure, mole fraction is what? 1. So the measured vapor pressure will be 1. Or sorry, not 1. 1 times 100, so 100 torr, because it's a pure water sample. But once we start adding salt to water, vapor pressure lowers. So that is part of colligative properties. That vapor pressure decreases for our saltwater sample because mole fraction is decreasing. And we're applying Raoult's law here, right? Okay, so then as our concentration becomes more salty, how does freezing point change? What's this property called? Freezing point depression. So freezing point decreases as we increase concentration of salt. Because the consequence is because vapor pressure is changing. And then finally, 2 more, boiling point, how does that change? Increases, and we can be getting this from the equations themselves. So delta T, freezing point is negative I mkf. Kf is a constant for water, but what we see, the concentration unit molality, that's what matters here. So we see as molality increases, this whole negative value increases as well. So our boiling point depression, that magnitude increases. Same idea for boiling point elevation. It's the same equation, it's just you use a different K constant. So I times M times KB. And again, as M increases, your change in boiling point increases as well, right? Both of those increase proportionally. And then finally, osmotic pressure. Does it increase or decrease for a saltwater solution as we make it more salty? It increases due to the equation, pi equals I molarity RT. So you can just see from this equation, as molarity increases, osmotic pressure for that solution increases as well. So those are the trends. Okay, so for any solution, we could calculate, mole fraction of water, vapor pressure, freezing point depression, boiling point elevation, given that concentration. Okay, so the question was, let's do vapor pressure. So let's do question 11. Okay, so in question 11, we have water and we have ethanol. Both of these are volatile. Both of these exert a vapor pressure on their own. So when we mix them together, both of them will contribute to the vapor pressure of the mixture. So we're using Raoult's law, where vapor pressure, I'm going to say total in our mixture, is equal to the vapor pressure that water exerts plus the vapor pressure that ethanol exerts. Right? Both of them are contributing because both of them are volatile. If the other solute was, let's say, salt, right? If it was salt, would we have to include vapor pressure of salt here? No, because it's not volatile, so we can just ignore that part of Raoult's law, right? But in this case, both of them are volatile. Okay, so in order to calculate the contributions of each of those components, we take the vapor pressure of each of these components in the pure phase, or the pure form, and we multiply it by the mole fraction of that component that's actually in this mixture. So let me just draw this picture. We have 3 moles of water in this mixture and 2 moles of ethanol. I tried to make the numbers really easy. All right, so this isn't a pure sample of water, it's not a pure sample of ethanol, it's a mixture. Both of them are contributing their own vapor pressures. So vapor pressure of ethanol in the mixture also is equal to the vapor pressure of ethanol in its pure form, but multiplied by the mole fraction of ethanol. All right, so what I like to do is read the question and see what variables do I already have, and then figure out what I need to calculate. So do we have, because we're trying to calculate what is the total vapor pressure of the mixture, do we have vapor pressure of water in its pure form? Yes, we do. It is 175. Do we have vapor pressure of ethanol in its pure form? Yes, we do. So it looks like all we need to calculate is mole fraction of water, mole fraction of ethanol. So to do that, we'll just go to the side here. Mole fraction of water is equal to moles of water in this sample divided by the total moles of stuff in this sample. So what is the mole fraction of water? How many moles of water in my sample? 3. And then what am I going to divide it by? 5, yes, because it's 2 plus 3, right? There's 5, and total here is 5. All right, so I think I can do that in my head. Is it 60%? Is it 60%? Good. All right, but using your intuition, what do you think the mole fraction of ethanol has to be? 40% or 0.4, whatever, as a fraction, but we can calculate it as well. There's only 2 moles of ethanol in this solution, but we're still dividing by 5 moles total. And so yes, we do in fact get 0.4. So it looks like this sample, the liquid part, 40% of the particles are ethanol, 60% of the particles are water. So we're going to incorporate those values into Raoult's law to see what our new total vapor pressure will be. So our mixture is going to have a vapor pressure between these 2 pure values. It's going to be somewhere between. And depending on what the ratio is, the mole fraction ratio, you'll be closer to one than the other. So it seems like we'll be closer to the water vapor pressure because there's more of it present. So at this point, it's just plug and chug. 175 torr. I'm going to drop the units because you guys are smart now. You made it through 1210. So 175 torr times 60% plus ethanol is 400 times 40%. All right, and what does my key say? It says this sample exerts a vapor pressure, P total. Let me just calculate what these components are. So water is contributing, this is 105 torr. All right, this component that's coming from ethanol, ethanol is contributing, I think, 160 torr. Yeah, that's right. Right, and so those 2 values up, those 2 contributions gives us a total vapor pressure of 265 torr. All right, so if we were to measure the gas sample above this solution, we should measure a total vapor pressure of 265 torr. All right, where 105 torr is coming from water, where 160 torr is coming from water. Or sorry, ethanol. Okay, So that is total vapor pressure of the solution. So a follow-up question that we can ask that is actually inherently a little harder is to ask about the composition of the vapor phase, of the vapor. We calculated mole fractions, but the mole fraction of what component of this picture? We calculated the mole fractions of components in the liquid phase. So B is not asking the same thing. It's not asking, I know it's asking mole fraction, but it's not referring to this mole fraction that we just calculated. That is the mole fraction of the liquid phase, the liquid phase. We want the mole fraction of ethanol in the vapor phase. So we want to use vapor values, all right? So the numbers that describe the vapor phase of this mixture that's sitting above it is what we just calculated already, where I told you that water is contributing 105 torr, that's coming from water. 160, that's ethanol's contribution, and it's giving a total vapor pressure of 265. So if we want to inspect the vapor phase, we have to use those pressures, those partial pressures instead. So to get the mole fraction of ethanol in the vapor phase, this is going to be a different number. We're going to take 160 torr and divide it by 265 torr. So note the numbers I picked. 260 torr is the vapor pressure of what in this Raoult law calculation? It's the vapor pressure contribution of ethanol. See how I use the ethanol mole fraction in the liquid form, its pure form? I'm taking 160 and dividing it by the total, right? So ethanol, what is that? If you do that, I think you get ethanol. Ethanol is actually contributing 60% of the vapor in this vapor phase. So we see ethanol in the vapor phase is 60% present versus in the liquid phase, it's only 0.4 present. All right. Should have picked better numbers where they don't exactly match. So if we just wanted to continue this, I know the question doesn't ask it, but what would be the mole fraction of water in the vapor phase then? It would be 40%, but you can also calculate it. How would you calculate it? It'd be 105 over 265. So be very cognizant when they're asking for mole fractions. Are they talking about the liquid phase? So you just go ahead and like calculate mole amounts, or are they talking about it in the vapor phase where you have to actually do Raoult's law, look at the different components and divide by the total vapor pressure, because those are all vapor values. Okay, so that is 11. Okay, how do we feel about that? Okay, all right, perfect. Okay, let's do anything else from colligative properties? Do we want to do 9 or 10? 9 or 10? No? Yes? Yes? Okay, so let's do 9. Okay, a solution of that in 50 grams of water freezes at this temperature. What is the molar mass in grams per mole, assuming this substance is a non-electrolyte? So this is freezing point depression. So recognize that we use the freezing point depression equation, negative I times M molality times KF, right? KF is given in the supplemental. I think it's 1.81. Is that right? 1.86. At least that's what my key says. I don't know what the supplemental information says. So that's a degrees Celsius per molal. All right, so lots of information given here. I always like to start with what is the question asking me to calculate? It's asking for molar mass of this compound. The unit of molar mass is grams per mole. So if I know the gram amount of this compound, and I know how many moles of compound I have, whatever, can I calculate the molar mass? Yeah, okay. Do we have one of these numbers already? Yeah, which one? Grams, cool. I like doing that because it makes me feel like I'm halfway done because I got grams already. Now I just need to figure out how many moles there are with all the other information. All right, so the gram of compound, what is it? Because there's 2 gram amounts here. Which one is it? It's The 2.5. This is the compound we're trying to figure out what the molar mass is. So it's 2.5 grams. All right. What is the molar mass of this compound if the solution freezes at this temperature? So the temperature water typically freezes at is what temperature? 0. So this value ends up being the freezing point depression because we're just subtracting from 0. So freezing point depression is negative 0.773 degrees Celsius. All right. Okay, so let's look at these other values. Did the question tell us what I was, the Van 't Hoff factor? Are you sure? All right, think about the different types of I's we have. Sugar. Sugar is a non-electrolyte. When you make a sugar water solution, does it conduct electricity? No, there's no ions in it at all. So sugar has a Van 't Hoff factor of 1 because when you put 1 particle of sugar in, you only get 1 particle of sugar out. But if you dissolve salt in water, does that conduct electricity? Yes, because when you put NaCl in water, do those NaCl things, do they stay together? Nah, you get what? When you put NaCl in water. Think about the net ionic equations and like think about, you know, is NaCl, do you split that for a net ionic equation? And then what do you split it into? NaCl splits up into sodium plus and chloride minus. So if you put 1 NaCl in, you get 2 ions out. So the Van 't Hoff factor for a salt like NaCl is 2. So the important piece of information in this question is it says this substance is a non-electrolyte. So what does that tell us about I? It's 1. Cool. So we got 1. We are solving for molality, and then we can just plug in that, that constant there. Right? And so here we are calculating what is the molality of the solution required to lower the freezing point this much. And so my key says that molality of the solution has to be 0.4156 molality. All right, so if we have a solution that has particle concentration of 0.4, we should see this freezing point depression for water. All right, so can I just put this number in my denominator? No, that's molality. That is moles. I need to somehow convert this into moles. So let's recall what the unit of molality is. It's different than molarity. Little m means moles of solute over what? Kilograms of solvent. Because big M, molarity, means what? Moles of solute over liters of solution. Yes, so it's different. So what this molality means, that we have 0.4156 moles of the compound in every 1 kilogram of solvent. That's what it means. So we're going to use that last piece of information that there is 50 grams of water present. We can convert that into kilograms, and then we can use molality. Again, I like to write my weird units into equalities so I can see how can I put the numbers in the numerator or denominator to get the number I want. So where is the 0.41 going to go in this fraction? Where's the 0.41 going to go? How can I set this up so I cancel the unit that I have right now? Grams cancels. I have kilograms of water right now. So I want to put which thing on the bottom and which thing on the top. 0.4 is going to go on the top. Yeah, so we're multiplying by molality. This isn't something to memorize. Just look at the units itself, right? Because you got to memorize enough things. Okay, so then 0.4156 moles of compound goes up top. And this is the mole amount that's present in the solution. I have my key. I could write it out. I can stop being lazy. There is 0.02078 moles of compound present in that 50 gram sample of water, given this molality. So we just put that number in the denominator, divide, then you're done. All right. So the next question is just like this. So note how we were given one component of molar mass already, grams. And to get the moles of the compound present, we had to use a colligative property, calculate molality, figure out the moles, put in the denominator. That's the same thing for question 10 as well, where I think we also want to calculate the molar mass, the molecular weight. We are given the weight of the sample, but this time we're going to use the osmotic pressure equation, pi equals I molarity RT. This question is operated the exact same. I already know the gram amount. I'm going to calculate the mole amount of sample I have using your osmotic pressure equation, where I think we solve for molarity, and we utilize the 25 milliliter sample that we have to get a mole amount, and you get your denominator. All right, so these are ways we can ask you to use colligative property calculations, but further it by asking you to calculate a property of a compound such as molar mass. Okay, all right. So let's, what do we want to do? 11, okay, you want to do 4, or do you want to do concentration conversions? Do we want to do that, or are those okay? Can we go over one? Yeah, let's go over one. Okay, let's do, let's do 6. Okay. All right, so we're given a molarity, and for some reason we're given a density, and we're calculating molality. Molarity and molality are different. So let's remind ourselves the difference. Molarity means moles of solute over what? Liters of solution. Little m means moles of solute over kilograms of solvent. Okay. So in this question, we are given a aqueous solution of, what is that? Potassium chromate. And I give you a density, and I want you to calculate molality of this solution. So how I always like to start is to remind myself what that molarity means if I needed to use it in a conversion factor. 0.872 molarity. What it means is that in my beaker, I have 0.872 moles of potassium chromate in every, how should I write this? In every 1 liter of solution. That's what I have. That's how I would use it in dimensional analysis. So maybe what can help is if you draw a picture, all right? We have a 1 liter solution. And in that solution, I also have 0.872 moles of potassium chromate. So we can look at this picture and ask ourselves, okay, how can I get the information in molality given this picture that I've drawn, all right? Because our goal is to get to a unit of molality. So let's think about this. Molality is moles of solute over kilograms of solvent. So if we look at this beaker, do we have a mole amount of solute in that beaker? Yes, we do. It is the 0.872. I like to kind of look at the units because look, we're halfway done. We have one of the numbers. We just need to figure out how many kilograms of solvent are there, right? But that's the hard part. So yes, we used the mole amount there. So it looks like we're gonna have to use the volume of solution. But am I using solution and solvent interchangeably, or do those have different meanings? They have different meanings. So a solution means your solvent and your solute. Solvent and your solute, all right? So when I say volume of solution, I'm actually talking about the volume of both the solvent and the solute. So this is where the density comes into play. I have the liter amount of solution, All right, so in 1 liter of this solution, we see the density given here. So 1 liter is actually 1,000 milliliters of solution. So if I use density, where 1 milliliter of this solution weighs 1.129 grams, we see that 1 liter or 1,000 milliliters of this solution weighs 1.129 grams of the solution. Cool. All right. So this gram amount, that's a mass. Can I put that in the denominator? No, because it's a gram amount converted to kilograms, right? No, look very carefully at the unit. The denominator for molality is solvent, but we just calculated the gram amount of, not the solvent, the solution. And the solution includes the gram amount of the solute and the gram amount of your solvent, both of those. So we need to figure out how much of that gram amount is the solute. And that's the number we're gonna put in the denominator for molality, all right? So if we figure out how much solute I have present, I can do a subtraction and just figure out how much of it's left for the solute. How on earth will we get the mass of solute present in this solution? What do we think? I gave you a mole amount. You know how many moles are there. Yeah, so the gram amount of solute comes from the 0.872 moles of potassium chromate that are present in this sample. So I gave you the molar mass. So in 1 mole, that weighs what, not 194.19. So the solute in this solution weighs 169.3 grams. And so that is how much the solute weighs. Our solution weighs 1,129. So that means our solvent is going to weigh 1,129 minus 169. So our solvent actually weighs 959.7 grams of H2O. That's how much is water. A very common mistake is students will just take that density value, but that tells you the gram amount of the solution. We need the kilogram amount of the solvent. So you got to do this subtraction. And so this is the number that you want to put in the denominator. Of course, convert it to kilograms before you do it. So molality here is going to be 0.9597 kilograms. Goes in the denominator, divide those things, you get your answer. All right. So I've told this in my class, how to approach concentration questions. These are the types of concentration questions we can ask you. X, what does that mean? Mole fraction. I can ask you mole fraction. I can ask you percent mass. And I can ask you molality. All of these things, and also like ppm and ppb, that's very close to percent mass. All of these units, you can interconvert them as much as you want, as long as you know the molar masses of your solute and your solvent. All right, you can interconvert those perfectly because mole amounts are additive. Gram amounts are additive, volume amounts are not. So that's why molarity lives on another island. And if you want to interconvert between units on different islands, you have to use what? Density. You only need density if you want to convert between molarity and any of these other units. But if you want to convert mole fraction to molality, you don't need density. If you need mass percent and want to go to mole fraction, don't need density. All you need are molar masses. But if you want to go to molarity, because the unit is moles of solute over liters of solution, you have to use density because volumes are not additive. Mole amounts are additive. If I have 1 mole of this, 1 mole of that, how many moles total do I have? 2. If I have 1 gram of this, 1 gram of this, how many grams do I have total? 2. But if I combine 1 liter of water and 1 liter of ethanol, do you think I'll get 2 liters of solution? You actually don't. Volumes are not additive. but gram amounts and mole amounts are. So that's why we got to use density to go between these two islands. All right? Okay. Great. So practice those. When is density needed? When is it not? Okay. So let's back it up. There was a question about Henry's law, so let's do that. Henry's law and solubility of gases. Okay. What are the general trends with solubilities of things? Solids. You know, if we try to dissolve a solid in water, we think about it, usually solids are more soluble at what temperature? Higher temperatures, yeah. We can use our intuition. Oftentimes we heat things up to get them to dissolve. So we see solid solubility increases if temperature increases, okay? The maximum of solid we can get into a solution increases if the water's hotter. But for gases, it's different. All right, gases, for the most part, do not want to stay in the water. They're highly energetic. So if you give a gas that's dissolved in water or in solution just a little bit of energy, it's going to leave that solution and go fly out into the atmosphere. Versus solids, they'll stay in that beaker. They stay in that beaker more so than water. Water evaporates over time, but solids do not. They just stay in the beaker. So gases have a tougher time staying dissolved in water. So what we see is that gas solubility actually decreases, decreases with increasing temperature, or gases are more soluble at low temperatures, all right? And the example I always give in class is, what do you enjoy drinking more, a room temperature soda or a cold soda? A cold soda. Have you ever drank a soda so cold that it's spicy? Do you know what I'm talking about? Like it burns you, because what's burning you? The dissolved CO2. That it's so cold, there's so much dissolved CO2 in there that it burns your tongue. And so we see that trend here, that gases are more soluble at lower temperatures. But think about it from a kinetic energy standpoint, less energy present in the sample for those gases to leave, right? So gas is more soluble at lower temperatures, more soluble. But also a property of gases is that the solubility increases when the pressure above that gas increases. When you open a brand new soda can, what does it sound like? What's that sound? Pressure. Cans of soda, they're packed under pressure, high pressure of CO2 to keep those gases inside. So the solubility, how much CO2 is dissolved in that soda can, is high when it's closed. But let's think about what happens over time to a soda. If you open it up and just leave it, what happens? It goes flat. Goes flat because now it's in contact with just one atmosphere of pressure. So nothing's keeping those gases inside, all right? So under higher pressure, gases become more soluble. So let's actually answer this question. Henry's law for helium is that. What is the solubility of helium in contact with one atmosphere of pressure, but the mole fraction of that gas, that pressure is only 0.25. So the equation for Henry's law is that the, solubility of a gas, essentially the concentration of that gas in solution, that's what that big S means. It just means concentration, it's in molarity, equals Henry's law constant for that gas times the partial pressure that in contact with that gas, the partial pressure of that gas in contact with that solution. Because, if we want to make a carbonated drink, we pack the pressure in the can with what gas? Can we use whatever gas we want? No, we want to use CO2. So if we are measuring the solubility of helium, we need to determine what is the partial pressure of helium in this sample. So, of helium, what is the partial pressure of helium in contact with this sample? Is the partial pressure of helium 1.5? No, that pressure is actually the total pressure. All right, so how do we get the partial pressure of just helium? Helium. I wrote xenon. We take total pressure, multiply by the 0.25. Yes, that only 25% of that sample is helium. So helium will exert a quarter of that pressure as its partial pressure. So X helium P total. Hopefully that equation looks familiar. It looks familiar, doesn't it? Yes. Because rearrange it. Remember how we calculated mole fraction in the gas phase? We rearrange things where mole fraction of helium is equal to partial pressure of helium over P total. Doesn't that look familiar? Yes? Okay. All right. So carrying on, 0.25 times 1.5. So helium exerts a partial pressure of the sample of 0.35 atm. And so that is the pressure that you want to put in there. You don't want to put in 1.5. We'd put in 1.5 if it was a pure sample of helium, but it's not pure. Only 25% of the particles are helium, so therefore only 25 of the particles will dissolve into solution. That value is given, it's 3.7 times 10 to the negative 4, multiply it, you're good to go, it's in molarity. And so you can see from Henry's law, all right, solubility of your gas will increase when will this value change? No, this is Henry's law constant, it's a constant, but if we increase the pressure that it's in contact with, like in a can of soda, solubility can change. But actually I lied, K can change. K, our Henry's law rate constant, is temperature dependent. So if we compared the K value of helium, Henry's law constant, at 10 degrees Celsius versus 50 degrees Celsius, at which temperature will K be larger? At 10 degrees or 50 degrees? 50 degrees? So the constant, you're saying that the gas is more soluble at higher temperatures. Yeah, whoops, no. Yeah, you see 50 and you think, oh, bigger number, bigger, yeah, no. So our trend with gases is gases are more soluble at cold temperatures. Cold sodas are tasty. Cold sodas are spicy because K is large at low temperatures versus at high temperatures, K is small. All right. Okay. All right. How are we with solutions? Okay. Okay. I'm going to just keep going. Did I do, I really don't want to do 4. Okay, yeah, we can do 15. Let me see, what is 12 and 13? 12, 13, 14, 15. Okay, let's do 12 and 13 first. Okay, I want to do ion pairing and stuff. Okay, so let's go back to colligative properties. Freezing point depression, delta T, this is 12, equals I M times KF. So I have aqueous solutions of all of these. Which one has the lowest freezing point? So remember, more solute particles, lower freezing point. So we're looking for the solution that has the most solute dissolved. So our strategy here is we're going to calculate what is the I times M product. Like we're going to multiply those numbers together to figure out how many, what's the concentration of solute particles. So yes, I have a bunch of equations or concentrations of things, but I don't actually have how many particles there are. All of these actually have the same molality. It's 0.1, 0.1, 0.1, 0.1, 0.1, 0.1. All of them have the same concentration, but they actually all also have different concentration of particles in solution because molality does not take into account the Van 't Hoff factor, right? So we need to actually look at the product. So the easiest way is to calculate determine what is the Van 't Hoff factor for all of these things. Pull from the depths of your brain net ionic equations. Think to yourself, these for the most part are electrolytes. When you put this compound in water and you have this in a net ionic equation, what ions come out? So when you put K2CrO4 in water, what ions do you get? You get K plus, but how many? 2 of them. And then how many chromates? Or yeah, and then what else do you get? 1 chromate. So note that chromate is no different than like nitrate. It stays, it stays together. Remember when you guys in 1210 try to split all of those polyatomics up? No, don't do that, all right? So you get 2 potassiums and an anion. So you put 1 potassium chromate in water, how many particles do you get out? 3, so I is 3. All right, sodium sulfate, what is the Van 't Hoff factor there? Also 3, because you get 2 sodiums, 1 sulfate out. All right, 3 particles. NaCl, 2, an Na plus, ACl minus, and then aluminum nitrate, 4, and then sucrose, 1. Sucrose is the only non-electrolyte. So you could put 1 sucrose in, you get 1 sucrose out. So what we want to do is actually look at the I times M product, because this will tell us the total concentration of total particles into solution. Because we said for every 1 unit of potassium chromate, we actually get 3 particles out. So the concentration of particles is actually 0.3 for potassium chromate. It's also 0.3 for sodium sulfate. It's 0.2 for NaCl, it's 0.4 for aluminum nitrate, and it's 0.1 for sucrose. So which one has the lowest freezing point? Aluminum. Which one has the highest freezing point? Sucrose, because there's the least amount of particles. Okay, how would I change the answer if I said which one has the highest boiling point? Sucrose? What is it called? It's freezing point depression, boiling point elevation. Yes, so if we want the highest boiling point, we're looking for the thing with the most or least particles. Most. So it would be highest boiling point would be the aluminum. Lowest boiling point, the one closest to regular water, would be sucrose, yes. Which one has the lowest vapor pressure? What is it? It's freezing point depression, boiling point elevation, vapor pressure lowering. So if I ask you for lowest vapor pressure, you're looking for the thing with what? The most or the least amount of particles? Most. Y'all, oh my gosh, we just talked about this. Vapor pressure for a mixture equals, let's say of water, is equal to water in its pure phase times the mole fraction of water. When will this value be the highest? When X is 1, when mole fraction is 1. But as soon as we start adding junk to water, mole fraction of water goes down. So lowest vapor pressure of these aqueous solutions is going to be the one with the most particles. So it's going to be aluminum nitrate. All right, because in this solution, mole fraction of water is the lowest because the mole fraction of the solute is the highest in this example because there's the most moles of stuff present, right? Okay, all right. Get off my soapbox there. All right, so that's Van 't Hoff factor predicting boiling point temperature, freezing point depression. You just look at the I times M product. So let me go one further. Do I want to do ion pairing? Sure, let's do ion pairing. Okay, so we calculated these Van 't Hoff factors for these compounds, but are these values always true? No, okay, because we're smarter in 1220. We look at all the weird exceptions, and so we see that there are certain scenarios where your Van 't Hoff factor is slightly lower than expected. All right, and that's called ion pairing. What ion pairing is, it lowers your Van 't Hoff factor. And so ion pairing, if you think about it, in a perfect world, what is the Van 't Hoff factor of NaCl? 2. Where you put one NaCl in, you get an Na plus and a Cl minus. You get 2 particles. But let's think about this. Na plus and Cl minus, they're cations and anions, right? Things that are positively charged and negatively charged. What kind of potential energy is this? This is what, attractions or repulsions? They're attracted to one another. So at a certain moment of time, a cation might graze an anion and they might just stick to one another for a moment, essentially lowering your Van't Hoff factor for a moment, right? So this is called ion pairing. It lowers your Van't Hoff factor. The idea is that, you know, we got these I's of more than one because there's ions present. But if your ions ever pair up, buddy up with one another because they're attracted to one another, you're going to observe a lower Van't Hoff factor than normal, all right? So if we look at this, let's just go ahead and calculate the I times M product for all of these, and we'll just see if anything weird happens. Okay, glycerin, what's the I for glycerin? 1. So its I times M is equal to exactly 0.2. All right, what about KCl? Has an I of 2, so that means its I times M product is also 0.2. Uh-oh. What about calcium sulfate? What is its I? 2, so what's its I times M? 0.2, uh-oh. And then calcium chloride, it has an I of 3, so finally it has an I times M of 0.3. So of these solutions, which one has the what? We're doing boiling point, highest boiling point temperature. This one. This one's the highest because that's the most particles. How the heck do we differentiate between these two? We use ion pairing. Yes. So when your I times N products are the same for two substances, you look further into ion pairing. We don't have to use ion pairing for this example because the I times M products, they're so different, they order themselves. But in this example, we have 3 things with the same I times M. So let's see if there's any deviations that can help us differentiate them. Okay. Use your intuition. Does glycerin exhibit ion pairing? Can it ion pair? No. Why? No ions. So it's glycerin's I times M, it's going to be exactly 0.2, exactly. But KCl, can KCl ion pair? Yes, because it's ionic. Can calcium sulfate ion pair? Yes, because it's ionic. We'll see which one can ion pair more. So the criteria for ion pairing is ion pairing's more apparent when concentration's high, but all of these have the same concentration, so we can ignore that one. The second one is when charges are high. Because the idea here is KCl is a +1 -1 cation anion. Calcium sulfate is +2 -2. In which one are the ions more attracted? Calcium sulfate or potassium chloride? Potassium sulfate. So +2 -2, there's more attractions. So ion pairing is going to be more apparent. So KCl does do ion pairing. So it's going to have a slightly less I times M than 0.2. It's going to be slightly less because its I is actually slightly less than 0.2. Right? But calcium sulfate, because it can ion pair more, it's going to be a lot less than 0.2, right? So a lot less than 0.2. And now we're able to rank these based upon boiling point temperature. So the solution with the least amount of particles in solution, therefore the lowest boiling point temperature is calcium sulfate, because that one ion pairs the most. Its Van't Hoff factor isn't very close to 2. Then it's going to be KCl, then it's going to be glycerin, and then the highest is going to be calcium chloride. All right, so that's ion pairing. All right, so let's, the question was question 15. Okay, I'll point out, I actually changed this question yesterday. So if you're looking at this and you have a something like a 30% decomposition reaction, I changed it because it was a question I did with my class already, so I had to change it. So I wrote this question instead. All right, so if you downloaded this packet today, then you're good. I changed this last night. Okay, so 15. Actually, let's just, since we're moving on to kinetics, we have 30 minutes left, let's just do kinetics. Let's just start at 14. All right, 14 is okay, I'm giving you the rate of something, like of a reactant. Tell me what is the rate of a different substance, like a reactant or product. So there's this long equation you can write out to get the relationships between rates of consumption of reactants, rates of production of products, or you can just use stoichiometry, right? Where for every 3 of these that are consumed, you have to make 2 of these at the same time. For every 2 of these that are consumed, you also have to make 2 of these at the same time. You can just use stoichiometry. So I'm giving you that the rate of appearance of, what is that? This thing, okay? Chromium 3 sulfate is 1.2 molarity or moles per minute. What is the rate of disappearance of a reactant? So in this case, it's this compound. So this is the relationship that I want to use. You can just go ahead and use stoichiometry, right? Where here's your rate, your velocity for one substance, so 1.24 moles of Cr2SO4, 3 of them, are produced every 1 minute. So if you look and kind of think about stoichiometry from, Chem 1210, you can use the coefficients. We're already in the unit of moles. So we can say, okay, for every 2 moles of Cr2SO4, 3 of them, how many C2H6Os do I have to consume at the same time? 3 moles of C2H6O. And so we see this 2 to 3 ratio, but check out how the units cancel, right? These units cancel. Now we're left with a rate of what we want. Moles of, this is ethanol per minute. All right, so whatever answer that is. Okay, so just take the value that's given, 3/2, because that's what the stoichiometry says. Right. If you do the long, drawn out equation, I guess I'll do that. The long drawn out equation says the rate of the overall reaction equals negative 1/3 change in C2H6O delta T. This right here, this thing, this is the rate that we're trying to calculate. That whole fraction, equals positive 1/2 change in Cr2SO4, 3 of them, over time. That whole thing is the rate of the appearance of that thing that's given in this equation. All right, so we can see, I'm just gonna take the absolute value of this right here. So we can get all the rates to be positive. If we put this 1.2 number in for that pink highlighted parenthesis, we will get the exact same answer for this yellow blob, right? This is the rate of disappearance of the reactant. Here's the rate of appearance of the product. So that's the number that we're putting in. You'll get the exact same answer. I honestly just like to use stoichiometry. You get the same answer. I don't even know why we teach this. Okay, so let's do 15. Yeah, well, this equation just confused. I got like 1 billion questions on homework just for this question, and it's honest. I don't even know why we teach it. Just use stoichiometry. Okay, I'm not saying why do we teach kinetics. I think kinetics are important. Kinetics is very important in industry because kinetics tells you how to make reactions go faster. Time is money. Right? We want to make more product. We want to sell more stuff. So it is important here. But yeah, just how we make these relationships, I think is not great use of brain space. Just use stoichiometry. So let's do 15, where, actually, before we move on, let me remind you that there are 3 ways to determine a rate law. 3 ways to determine a rate law. The first way is the method of initial rates, right? We can only ever find a rate law experimentally. We can't just look at a reaction and know the rate law. We have to find it experimentally. And the reason is because, yes, I can write out a reaction, but can you see atoms colliding and reacting with each other? No. So we actually have to look at experimental data to see if it's consistent with the rate law that we proposed. So the first way we can get a rate law is method of initial rates. The second way is using the integrated rate laws and graphing. Right, graphing. You'll do this in the bar lab. Bar comes after FPD. So you do FPD this week, bar next week. Or no, I think you have an off week. Yeah, off week, and then bar, which is photo bleaching of allure red. You're gonna bleach red food coloring and determine what the order is. Okay, all right, and then the third way we can get a rate law is how? At least my class learned it. It's our favorite one. It's mechanisms, yeah. So these are the only three ways that we can get a rate law. All right, mechanisms is not on midterm 2, or sorry, 1. It's on midterm 2. So let's look at this question. When do we use what? Method of initial rates is when I tell you, like, you double this concentration, you see a ×4 increase in initial rate. If you ×5 this concentration and you see no increase in initial rate, that's method of initial rates. This question is not talking about that. It's talking about time and concentration data. So I want you to recognize when time is involved, that's when you use the integrated rate laws. So this is method 2, where we are using the integrated rate law. So I like this question. I wrote it myself. And if I find it on Chegg, I'm gonna be real mad. All right, so we have radioactive decay of technetium-99. So this is for you health people out there, I guess. It follows first order kinetics. So we should know that all radioactive decay follows first order kinetics. But I tell you, technetium is a radioactive isotope tracer that they give to patients so they can take images of their heart. Right? So you like ingest it or they inject it, I have no idea, but it like goes to their heart and they can take images that basically light up their heart with this radio tracer. All right, so, and it follows first order kinetics. So a patient is dosed with technetium-99 and goes for a heart scan. But they notice, they do another scan 12 hours later, and the image loses 75% of its intensity. What is the half-life of technetium-99? Okay, so I'm giving you, I didn't really give you concentration, but I want you to recognize if technetium-99 is a isotope, a radioactive isotope tracer, its presence is what causes for the image. We can infer what the concentration changes are. If the image loses 75% of its intensity, how much of the sample did we lose? Probably 75%. So that means the concentration after some time, if I lose 75%, is what? Is it 75%? No, it's actually 25%. Because how much did I start with? 100%, yes. And so this idea, I lost 75% of my sample, right? So this was a fancy way of me saying you lost 75% of your sample, but I tried to make it more health-based. I tried. And how long did it take to do this? 12 hours, great. Okay. So there's two ways to do this problem. The easy way, but it's the lazy way. Or you can do it the right way, but it's a little longer. Which one do you want to do? Lazy way? But let's do it both ways, okay? Let's do it both ways. So first order kinetics is the only one. So if you look at the supplemental information, first order kinetics is the only one where half-life is not dependent on concentration. This half-life, this is zeroth order kinetics. The half-life for a zeroth order reaction depends on concentration. The half-life equation for a second order reaction also depends on concentration. But the half-life for a first order reaction does not depend on concentration. All it depends on is K. So here is the lazy way. It's not the lazy way. It's, okay, let's just use our intuition. Okay, if we start with 100% of our sample and one half-life goes by, how much sample do I have left? 50%. Very good. Okay, so if now we have 50% of our sample, what if another half-life goes by? 25%. So how many half-lives does it require to lose 75% of your sample? 2 half-lives. So if 2 half-lives equals 12 hours, it takes 12 hours for 2 half-lives to go by. How long is 1 half-life? It's 6 hours. All right, that is the lazy way. All right, why is it the lazy way? I gave you super easy numbers. That's why. I just gave you super easy numbers. So let's do it the right way, and that's using the integrated rate law, where we will always get the right answer, always, regardless if the numbers are like easy or not. It'll always work every single time. So this is how we do it with the integrated rate law. So we actually have all the information we need. When 12 hours goes by, our sample goes from 100% to 25%. So if we look at the integrated rate law, natural log of stuff at some time equals natural log of A sub 0, so that's the initial concentration, minus KT. Do we have all the variables to calculate rate constant? Yes, we do. We have A sub t, we have A sub 0, we have a time it takes to do that. So we can plug all these numbers in and get rate constant. All right, so let's just do that. Natural log of 25 equals natural log of 100 minus k, that's what we're solving for, times t, so times 12 hours. All right, so I know that these are percentages, but regardless if you put 25 and 100 or 0.25 and 1, you will get the same answer, I promise. I just am lazy and don't feel like writing decimal places. Okay, so if you solve for that, you get that the rate constant of this reaction is 0.1155 hours to the negative 1. Is that my half-life? No, I got to do one more equation. So I want to tell you the significance of a half-life. The reason we report like decay sequences in half-life is because it makes more sense to us intuitively. It makes sense that, okay, this sample, you lose half of it in 6 hours. We can, as humans, we can wrap our heads around what that means. But if I tell you that this reaction has a rate constant of 0.1155 hour to the negative 1, do you know how fast that is? Do you even know what that means in terms of how fast this reaction is? I don't. I have no idea what that means, but I do know what a half-life means. So let's convert this to half-life to see if that number that comes out is more meaningful to us. So T1/2 is equal to natural log of 2 over the K we just got, 0.1155 hour to the negative 1. Yes, I know in your supplemental information it says 0.693, but just put natural log of 2 in your calculator. What is it? 0.693. I don't like that they put 0.693 because it looks like we just pulled that number out of our butt. What it is actually just natural log of 2 that comes out of the integrated rate law. Okay, so you put that in your calculator and someone tell me what you get. 6. So what makes, I don't know, what makes sense to you? What like has meaning to you? Does this number mean anything to you? No, it's just a number with a unit. But does T1/2 equals 6 hours mean something to you? Yes, that makes sense. It's like, yeah, I lose half my sample in 6 hours. So here's the moral of the story. Yes, this is the lazy way. But why does it work? It only works because the numbers are easy. That's the only reason why it works. You can always use the integrated rate law. I could give you concentration change for, 100% to like 33%, and you could still get K, get T1/2. All right. So the integrated rate law will always work. So I don't know, what do you like more, the lazy way or the integrated rate law? The integrated rate law, I like it better. Just get K, and then convert it to T1/2 so it makes sense. Okay. All right, so there's that one. So that was integrated rate law. Let's do one more integrated rate law. Okay, I also wrote this question. The consumption of donuts by Homer Simpson has a rate constant of 5 donuts per minute. How many donuts are left after 4 hours if Homer starts with 100, that many donuts? See, when I wrote this question, I was imagining the episode where Homer is in hell and they're force feeding him donuts at a certain rate. And I was assuming it was 0th order. So that's what I thought about in this question. So anyway, I hope you see that there is a rate constant, there is time, there is concentrations, donuts is our concentration. So I hope you can see that this is the integrated rate law, right? But what's the problem? The last reaction I told you is 1st order, but this one I tell you what the order is? No, I don't. So does that mean we can't answer the question? We actually can answer the question. Oh, poo. And it's from the rate constant that's given, the unit of the rate constant. Yes, so the unit of the rate constant is donuts per minute. So let's look at the unit of the rate constant for a 1st order reaction. It's a inverse time, right? So just looking at comparing these 2 units, is this reaction 1st order? No, it's not. So let's determine how we figure out the reaction order given a rate constant. So this is the strategy. You don't have to memorize it, I promise. If you think about a generic rate law, that's 0th order. Rate equals what for a 0th order reaction? K, rate constant, times concentration of something to the 0, which is 1, right? So you're not multiplying by anything. Rate has a unit of molarity per second. So for a 0th order reaction, what is the unit of K have to be so rate ends up being molarity per second? It has to be molarity per second. So this is a 0th order K rate constant. You get it from the rate law. Okay, so then how do we get a rate constant for a 1st order reaction? Just write the rate law. Rate equals rate constant, but how many molarities do we multiply by? Just one of them. So this is how I like to think of it. Rate has to be molarity per second equals a rate constant times a molarity. So I asked myself, what does the unit of K have to be so rate ends up being molarity per second? It has to be a inverse time, so per second. All right, so that is the unit of K in a 1st order reaction. All right, so then what about a 2nd order reaction? We write the rate law for a 2nd order reaction, just a generic one. Rate equals K, but how many molarity units do you multiply by? 2 of them, so it's molarity squared. And then you ask yourself, what does the unit of K have to be so rate ends up being molarity per second? This one's a little trickier. I need a molarity on the bottom, so one of them cancels, and I need a 2nd on the bottom. So there's a 2nd there. So for a 2nd order, K has a unit of molarity to the -1, 2nd to the -1. Yeah, and that's how you get it, right? So you can get it on the fly if you're good with units like that, or I mean, there's only 3 of them. I guess you could memorize them too, but you don't have to. So based upon what we just went over, this, that, for a 2nd order, what do we think this rate constant is? 0th order, because donuts, it's like number of particles, essentially. It's concentration. This is a 0th order reaction. Perfect. So now we know what integrated rate law to use. All right, it's donuts per minute. So 0th order is concentration of stuff at a certain time, in this case donuts, equals, I don't even know what it is. What is it? Yeah, concentration at some time is concentration initially minus KT. So this question, I tell you K, we got the order, we had to get it ourselves. How many donuts will be left after 4 hours? So 4 is K, T, time. And then 1,800 donuts, what variable is that? Concentration, but concentration sub 0. Yeah, so this is A sub 0. Yeah. And what are we solving for? A sub T, how much we're left over with. So it's A sub T equals how much we start with minus K, so 5 donuts per minute. But we have a problem. Can we just put 4 hours in the T? No, we got to convert that. So 4 hours, turn it into minutes. That's probably the easiest way. 4 hours, 60 minutes. I think I can do that in my head. 240 minutes. So 240 minutes is our T. And so we see units cancel, minutes cancel. So we're subtracting 1,800 donuts by this multiplication thing. And I think you get that Homer eats 5 times 240. In 4 hours, he eats 1,200 donuts. Okay, donuts. So then that means there will be 650 donuts left. So this 0th order reaction is really no difference than like how you calculate distance and velocity, I like to think. This rate is essentially a velocity. Donuts per minute, that sounds like distance per minute, right? Yeah, and we're subtracting it from where we start, taking a velocity, multiplying it by time, and that's how much we move. So yeah, this 0th order is really like, kind of like a velocity question, right? Okay, so let's do 19, or someone asked about, I wanna do, okay, we have 13 minutes. Okay, let's just do 17. All right. Okay, so those were integrated rate laws. How else can we ask rate laws? We can just give you the order. So consider a reaction that's first order with respect to A, 0th order to respect to B. You should be able to write the rate law. So for that first sentence, what is the rate law? Rate equals a constant times what? A to the 1, and then what else? Or is that it? That's it, yeah. So even though if I look at this reaction, it's A plus B gives us C, I can't just take those reactants and turn them into a rate law. You can only do that for mechanisms. I straight up told you it is first order with respect to A, 0th order with respect to B, so B is not in our rate law. Okay, so I tell you that this reaction has this rate when A is that concentration, B is that concentration. What is the reaction rate when A is this concentration and B is the other concentration? So I am giving you a rate at a given concentration, figure out the rate at the new concentration. So the intermediate between these two steps is given these first conditions, so 0.525 and that A concentration, I can actually calculate what is the rate constant for this reaction. Once I have the rate constant, I can plug in the second set of numbers that are given, right? So those pink values I'm gonna plug in. The rate is 0.525 molarity per second equals K rate constant when A has a concentration of 0.100 molarity. Do I have to put B in here at all? No, B is actually a distractor because it's 0th order. I didn't have to put it in there, but I did because I wanted to trick you, right? But I told you it's 0th order, so I don't have to put it in there. So we see, I think I can do this math myself, that K is equal to 5.25, second to the -1. Perfect, so we can stick that K back into our rate law, and now we can calculate the new reaction rate with this new concentration. And that's basically it. Do we have to use B? No, we don't. So the new reaction rate is equal to that K we just got, so 5.25, second to the -1, times 0.250. molarity. And so you see the rate you get out is molarity per second. All right, so whatever that is. Okay. 17. All right, let's do, I think, yeah, we have enough time to do these last two. Okay. So that was rate law. The rate law, where we give you certain aspects of it and we calculate K, figure out the new rate. So the last way, or the other way that we can ask you to determine a rate law, is using the method of initial rates. So we should be using our intuition a little bit here. We're changing the initial concentrations of reactants and observing how does the reaction rate change. At the beginning of chapter 14, hopefully to kind of get you acquainted with how reactions, why they occur, how fast they occur, we've thought about some different factors. Collisions affect reaction rate. Your reactants will collide more if concentrations are high. So the thought is, if I double the concentration of something and I see a doubling of rate, to me, that's a kind of 1-to-1 ratio. So I can say that that reactant is first order for that reaction. Versus if I have a doubling of concentration, but I see a 4-fold increase in rate, does that mean first order? No, it means second order. That's what we're looking for here in the method of initial rates, where we look at 2 experiments where only one thing changes. We want to focus on when one thing changes, because that's how we can isolate that reaction order. So I see that experiments 1 and 2, O2 concentration stays the same. But what is happening to the NO concentration? It's, hopefully you can do this in your head, it's changing how? Times 2. Yes, it's doubling. Then what's happening to that reaction rate? Okay, this you might have to put in your calculator. It's increasing by what fold? What factor? 4. So tell me, what does that imply about the order? It's second order, because 2 squared is 4. So, but what is second order? Which reactant is second order? Any of them? No, it's the NO concentration one. Yeah, so this implies NO concentration is second order, because that's the one that's changing between experiments 1 and 2. Okay, cool, we're halfway done. So experiments 1 and 2 got us NO order. What 2 experiments will help us get the O2 order? Experiments 2 and 3, because there NO stays constant. And O2 changes. So how does O2 change for, no, not that experiment, this one, these 2. What's happening? It's doubling, and then what's happening to the overall rate? This one's a little harder because of the scientific notation. You can think of this as 11.3 because of the exponent. So it's doubling. So what's the order of O2? First order. So O2 is first order. All right, so there's basically our rate law. So the full rate law for this reaction is rate equals K times NO concentration squared O2 concentration just to the 1. Actually, I lied. Is this the full rate law? No, we just have the orders. What else do we need to complete this rate law? K, the value of K. How do we get that? You take any experiment and you plug in the numbers. So which experiment do you want to use? No, be weird with me. 3, yeah, let's use experiment 3. All right, so let's take the data from experiment 3, plug in the numbers, and then calculate what K has to be. But here's the thing, does it matter which experiment you use? No, as long as you got the correct rate law, it doesn't matter whether you use experiments 1, 2, or 3, you will get the same answer, I promise. So rate equals 1.13 times 10 to the negative 1 molarity per second. We're solving for K. NO concentration, so 0.0252 squared times 0.025 to the 1. And then we get K equals something. K equals a tiny number. Oh no, a big number. 7.1 times 10 to the 3. Molarity to the -2 second to the -1. Oh, I got lazy. I didn't put my units. Yikes. Molarity and a molarity there. So total, this reaction is third order. So there's a total of 3 molarities. And so you see that the unit of K has to have 2 molarities in the denominator to cancel all those out. So you get molarity per second as your rate. So that is K. Our full rate law will include K in the third order business up there. Would they want K from one experiment or the average of 3? So the idea here is I asked, which experiment do you want to use to calculate K? And really the reason I asked, because it doesn't matter which one. If you do any of these, so I implore you, I used experiment 3, but if you use experiment 1 or 2, you will get the same answer. The same answer, doesn't matter which one you use. So you don't have to take the average because any of them will work. And so prove it to yourself. Please prove it to yourself that if you plug in the information from any one of those 3 experiments, you get the same exact K for all of them. And that should make sense because this is the same exact reaction. So if you think that you will get a different K for each of these different conditions, do review what rate constant means. This is a constant for this specific reaction. Okay. So let's finish this question and then do 19. Okay, so calculate the overall initial rate with these concentrations. So what's my strategy here? Just plug them in. Yeah, we already got K. Yeah, so just plug these new numbers into the rate constant, and that's it. That's it. So we're just going to do a fourth experiment that has these new concentrations, and we would just plug that into the rate law. Okay. So that's how you would do B, just plug in the numbers. You already have the full rate law. Okay, so everyone wants 19. So here in question 19, this also has to do with reaction kinetics because we talked about ways we can make reactions go faster. One of those is heating the reaction up, right? But when we heat a reaction up, why does the reaction go faster? Why? It's because at higher temperatures, there's more kinetic energy. Your particles now have more energy to collide and go over your activation energy, the activation barrier. When you heat up a reaction, does the activation energy change? Does the height of the hill change? No. But you change how much energy particles have to go over that hill. That's what changes. And so that's when we use the 2-point Arrhenius equation. And I want you to recognize we use the 2-point, so there's 2 forms of the Arrhenius equation. This one, K equals A E negative EA over RT. Okay, you're gonna never use that equation. Never do we just straight up plug numbers in and calculate K. That's not really what we do. But from that equation, this is how you get trends. That K will increase when temperature increases, or when activation energy decreases, or when effective collisions increase. We can see the trends for rate constant. But experimentally, how we determine rate constant is either using the linear form of the Arrhenius equation or the 2-point form of the Arrhenius equation, because 2 points will always make a line where they're related by activation energy. So the 2-point Arrhenius equation says natural log of the ratio of K1 over K2 equals EA over R, T2 to the -1 minus T1 to the -1. Those are just 1 over temperatures. All right. So what I want you to recognize is that you have a temperature, T1, and a rate constant at that temperature. You have a second temperature and another rate constant at that temperature. So as long as you have 2 temperature points two rate constants, you can calculate activation energy out of that, all right? But in this equation, we're doing it a little bit differently, where actually I give you activation energy, I give you two temperatures, I give you one of the rate constants. I want you to just calculate what's that missing piece, all right? But use your intuition a little bit. If at 25 degrees, this reaction has a rate constant of 0.15 molarity per second, what is the rate constant at 75 degrees? Is the rate constant going to increase, decrease, or stay the same? Hot reactions go faster, so rate constant should increase, yes. So given this information, 25 degrees, that is T1. T1 equals what, 298 Kelvin? 0.15 molarity per second, that is K1. T2 is 75 degrees Celsius. I think, what is that? T2 is, what is it? 348 Kelvin. And I'm asking, what is that new rate constant at that new temperature? So here's activation energy. It's 95 kilojoules per mole. But the important note in the integrated, the 2-point Arrhenius equation is that we're dividing by R. Which R are we using? 8.314, what's the unit of that? Joule, mole, Kelvin. So that means activation energy. Can it stay in kilojoules per mole? No, you have to put it in joules per mole. So 95 times 10 to the 3 joules per mole is what we'll put in. So putting this all together, it's natural log of 0.150 molarity per second over X. I'm solving for K2 equals 95 times 10 to the 3 R 8.314 T2. So be very careful of your temperatures. T2 I defined as the high temperature one. So 348 Kelvin to the -1 minus the lower temperature one, 298 Kelvin to the -1. All right. So there's one variable, we can solve for it. So if you do the whole thing on this side of the equation, you get something like -5.509 ln 0.15 over X. How do I get that X out of that natural log? You e to the both sides, yes. So if you take e to the -5.509, you get 0.00405. And so that undoes the natural log. So now you have 0.15 over X. And so you can put the X on one side, divide 0.15 by this tiny number, and you get that X is equal to 37 molarity per second. All right, and so that X is K2, or the rate constant at the higher temperature one. So for those of you that are still with me, does that answer, oh, you can't see it, sorry. Does that answer make sense intuitively? We heated the reaction up, rate constant should go up. Did it go up? Yes, it did. Very good. All right. Best of luck.